Hello, everyone. This is Nobuhiro Yanai from Kyushu University, Japan. So first of all, I'd like to thank all the organizers of this symposium meeting to give me this great opportunity to share a recent result with you. Uh, uh, so today I want to share our works on the photon upconversion in solid materials, especially with the emphasis on the control of the exciton dynamics. So if it's unfortunate that I cannot meet in person, and also I cannot join the live session because of the big time difference. So now it's midnight in Japan. So I'm going to show you this recorded video, and if you have any question, please email me or contact me later. Okay, so the photon upconversion is a process that converts from the longer wavelengths to the shorter wavelengths. So in terms of energy, it's from the lower energy to the higher energy. So it can be useful for many applications from energy to biology. So all these, especially for the energy applications, all these solar power devices like photocatalysis, photochemical synthesis, and photovoltaics, they are limited by wavelengths. So the subband gap photons are just wasted. So if you can upconvert these wasted photons, you can improve the efficiency of all these devices. And also near-field light is known to have a good transparency in biological tissues. So if you can convert the near-field light into the visible light in the body, you can use it as an internal light source. So there are a few upconversion mechanisms, and that includes the two-photon absorption and multi-step excitation of lanthanides. But unfortunately, they're very useful for biological imaging, but unfortunately, they require strong excitation light, like over watt per square centimeter. So if you think about the solar irradiance is 100 milliwatt per square centimeter for all the wavelength range. So it cannot give you the high quantum yield, upconversion quantum yield at such low excitation intensity. So instead, people have recently seen this tube-to-tube annihilation TTA-based upconversion. It was first demonstrated by Parker and Hatcher in 1962, and it gains renewed attention these days because it can be useful for the solar applications. And the biggest advantage of this molecular system against the other mechanism is that it works at the weak excitation intensity, like sunlight, solar radiance. And also its efficiency can be high. This most basic popular combination of donor and acceptor gives the 40% of efficiency among the 100% of maximum. Okay, so this the platinum octative porphyrin PTOEP and diphenyl anthracene DPA are the most basic combination, and they give you the green to blue upconversion. By shining the green light, you can see the nice blue upconverted emission. Okay, so by taking these two donor and acceptor, let me briefly explain the mechanism of this TTA-based upconversion, or also called as stupid diffusion upconversion. So first, donor PTOP absorbs the light and undergoes the intersystem crossing to become a tubet state, and this tubet energy is transferred to this acceptor tubet by the TT, tubet energy transfer process. This is Dex energy transfer process. And these sensitized acceptor tubets again meet to undergo TTA, to form one higher energy singlet state, and one goes back to the ground state. And eventually you can get upconverted emission from this S1. So basically you absorb two photons to emit one high energy photon. And to do that, you need to have 2 times of the tubet energy transfer, and also 1 time of the inter-accepted TTA. So to achieve these 3 times of text energy transfer during the lifetime, people usually use the molecular diffusion in solution or soft polymer. So you have the soup of donor and acceptor, and you shine the light, and the donor also and then transfer the energy to the acceptor, and you populate acceptor triplets, and then these acceptor triplets finally meets to short upconversion. But we have been proposing to shift from this molecular diffusion to the energy migration. So in this dense assembly of acceptor doped with donor, donor transfer the energy to the neighboring acceptor, and this sensitized acceptor exciton can diffuse to show the upconversion. But why we need to do that? Because we see a few severe problems in this molecular diffusion-based upconversion. Of course, you need to have the first diffusion constant of molecules, so you need to use the volatile, very volatile solvents with low viscosity. And you can use like soft polymer, but in that case, the molecular diffusion is not as high as, not as fast as in the solvents. And to solve these issues, we have been proposing to shift to this energy migration or exciton diffusion in condensed systems, because now you don't need any solvents, and also you can get the first exciton diffusion in the dense assembly. So with this strategy, we have systematically studied many different molecular assembly systems. So we are the synthetic material chemists, so we can make many different types of materials, from the molecular liquid to ionic liquid to supramolecular gel assembly or molecular glass, liquid crystals, and many of them are the first examples showing upconversion. So today I want to share a few examples among them. Especially, I want to discuss the importance of exciton dynamics in these molecular assemblies. Okay, the first topic of today is the epoxy resin. Actually, the epoxy resin is the very popular material as a sealing, for example, in OLED, because it has the excellent oxygen blocking ability or low diffusion constant of molecular oxygen in the epoxy resin, so that you can avoid degradation. So we actually add the donor and acceptor chromophores directly in the epoxy material matrix. So we took this PTOP, the common donor, and then as acceptor, we modify the DPA with sulfonate and make the ionic liquid by ion pairing with this flexible phosphonium cation. So we use this ionic liquid acceptor because it can be dispersed without phase separation up to very high concentration, like 1,000 millimolar, so 1 molar. So if you use the normal conventional DPA, it phase separate and crystallize precipitates in the epoxy, the film. So you cannot get a transparent film, but with this ionic liquid, you can get very transparent film. And glass transition temperature is still above the room temperature, so it's rigid at room temperature. So you need such a high concentration, 1,000 millimolar, 1 molar, because by doing that, you can get enough short inter-acceptor distance of 0.87 nanometer, less than 1 nanometer. So it's short enough for the triplet exchange transfer. So actually, with this rigid film, we shine the green laser, and we observed nice green to blue upconversion in air. So, and the efficiency is kind of good, so 3.8%. So, but when we reduce the acceptor concentration from 1,000 millimolar to 100 millimolar, the efficiency dramatically drops to 0.09%. And we cut the phosphorescence by short pass filter, but actually we observed a very strong phosphorescence. So the donor to acceptor triplet transfer is not efficient, so that eventually upconversion efficiency was very poor. So actually you need such a high concentration of acceptor, not only for the triplet exciton diffusion between the acceptor, but also the triplet transfer from donor to acceptor. Okay, so then we recently have some more updates on this system. So here we use not only in addition to this ionic liquid type of acceptor, we also incorporate this acceptor unit covalently in the epoxy network. So now we have two types of acceptor, one ionic liquid and one in the network, polymer network. So again, we use the same donor PTOP, and we first make the liquid precursor, that is a mixture of all of them. And by just heating at 100 degrees C and 150 degrees C, we obtain this rigid cured epoxy uridine. And by shining the green laser, again, we could observe nice blue upconverted emission in air. So now the acceptor concentration is further increased, and now that we observe no donor phosphorescence. So, and tribute energy transfer is almost 100%. And of course, we observe nice upconversion in blue region. And importantly, this gives us the high efficiency, upconversion efficiency of 11.4%. And this is actually the highest TT upconversion efficiency for rigid polymer material. You can get higher with a soft material, but it was quite difficult to achieve such a high efficiency in the rigid polymer material. I mean, rigid is the glass central temperature is higher than room temperature, and there are almost no molecular, free diffusion at room temperature. So purely Exciton diffusion process. So, and another important feature here is that, epoxy resin have a good oxygen blocking ability, so that we observe almost same upconversion efficiency between the epoxy resin prepared in air or prepared in nitrogen-filled grow blocks. Okay, so to understand such a high efficiency, we systematically changed the acceptor concentration. So we keep the concentration of this ionic liquid acceptor, and we changed the concentration of this acceptor in the epoxy network. So by changing the ratio between the epoxy with and without the acceptor unit, we could tune the acceptor concentration from 35 weight% to the 17 weight%. So we observe the high upconversion efficiency over 10% when the acceptor concentration is above the 30 weight%. And when we reduce the acceptor concentration, we observe the decrease of upconversion efficiency to 4%. Well, actually, the donor phosphorescence was observed at 4 weight%. So tribute energy transfer is not perfect, but it's already efficient. It's over 90%. So most of energy is already transferred, except so this cannot explain such a big difference. So there should be some other reasons. So to understand this difference, we measure the phosphorescence decay, that is the donor phosphorescence. So this red curve shows the only PTOEP in the epoxy resin. And when we add the acceptor and by increasing the concentration, we observe these different decay curves. So at 17 weight% of acceptor, we observed the decrease of the donor phosphorescence. This is because of the partial quenching of the donor phosphorescence by acceptor. But in addition to that, we also observed the long tail here. Actually, the lifetime of this long tail corresponds to the acceptor triplet lifetime. So this telling us that the after in triplet energy transfer, the back energy transfer from acceptor to donor also happens, and it gives the delayed phosphorescence from the donor. But by increasing the acceptor concentration from 17% to 34%, we observe the much more energy transfer and also suppression of this long tail. so that at such high concentration of acceptor, the back energy transfer from donor from acceptor to donor was suppressed. So to get deeper insight, we estimated the diffusion constant, apparent diffusion constant from other upconversion parameters like threshold excitation intensity and triplet lifetime. So this is not a monotonic simple relationship. So we cannot explain everything from the diffusion constant, but we consider that increase of diffusion constant partially contribute to this improvement of upconversion efficiency. We are thinking this way. So with at the lower concentration of 17%, the triplet diffusion is not very fast, so that after energy transfer, triplet cannot move away quickly. So it's going back, and then eventually some goes back to the donor. But with the high triplet diffusion, at higher acceptor concentration, triplet can diffuse faster, so it can escape from the donor and then undergoes the TTA before going back to the donor. Okay, so this acceptor concentration above 38% in this such amorphous network is in rigid network is very important. So if you have such a high concentration, you can get a nice upconversion even in the rigid film without molecular diffusion. And another very important feature of this epoxy resin is the excellent processability. So by just spin coating, you can get the nanofilm and with a thickness of 300 nanometer. And this again shows nice upconversion in air thanks to the good oxygen blocking ability of the epoxy resin. And you can mold into more complex shape. And here is a micro lens shape, and you can get upconversion in this micro lens. Okay, so next I want to show you some another example. Like that is not only the triplet back energy transfer, but also the singlet back energy transfer is also the severe issue in the solid upconversion materials. So this is the collaboration work with Queen at UC Santa Barbara. So when we use only donor and acceptor, so donor is PTOP, acceptor is this Anderson derivative. Actually, this is the crystalline, this forms the crystalline film by spin coating. So by spin coating this mixture, donor acceptor mixture, we observe the severe back energy transfer, but by just adding this collector, we found that back energy transfer can be avoided. So this two-component donor acceptor system show the 4% of upconversion efficiency, and by just adding the small amount of collector, we observe the more than 2 times higher upconversion efficiency. So this is partly because of the improve of fluorescence contaminate, as pointed out by Baudo's group in 2015. So the originally only acceptor film shows the fluorescence contaminate of 34%, and it increases to 70%, 71% by adding this collector. So you can avoid, kind of concentration quenching by using this isolated collector. But more importantly, we observed the suppression of singlet back energy transfer by collector. So in the two-component donor acceptor system, we observe 40% of back energy transfer, but by adding the collector, such back energy transfer did not almost happen. This is because the donor and the collector is in the low concentration, so their average distance is farther than the FRET radius, so that back energy transfer can be almost avoided. So thanks because of this suppression of back-energy transfer and also improved fluorescence quantum, we could observe the higher upconversion efficiency. So my last topic today is the near-infrared to the visible upconversion. So so it was difficult to upconvert the near-infrared to the visible because of the energy loss during the intersystem crossing from S1 to T1 of the donor. So we propose to use the ST absorption, that is the direct transition from the ground state to the triple state. So you can skip the intersystem crossing, so you can avoid the energy loss. So we synthesized this osmium complex. This shows a nice near-infrared ST absorption thanks to the heavy metal effect of the osmium ion. And we combine this osmium complex with Lubrin acceptor. So now we prepare the Lubrin amorphous nanoparticle and doped the osmium complex into this Lubrin nanoparticle. And then we disperse this in the PVA film that has the good oxygen blocking ability. So by shining the invisible near-infrared light to this film, we observe the nice yellow upconverted emission in air. So although Militant's group and then Baudo's group showed a nice near-infrared to visible upconversion by using the semiconductor in organic nanocrystals, here we show the first example of purely molecular system that can upconvert the near-infrared over 9 nanometer. So, this two-component film system shows the not high upconversion efficiency of 0.43%, but again, by just adding this third component collector, we could enhance the efficiency to 4.1%. And why is that? So, as I already mentioned, this fluorescence quantum can be improved by using the isolated this collector DBP. And also, similar to the previous PTOEP antecedent derivative system, back energy transfer is largely avoided. And also, experimentally, we found that this singlet energy collection process is very selective against the back energy transfer because of the larger Fred constant from acceptor to collector than the acceptor to the donor. And at last but not least, the Lubrin singlet is about energy level is about 2 times of the triplet. So not only the TTA, but also the singlet fission can happen. So people have assumed that this singlet energy collection can outcompete with this singlet fission, but by collaborating with Jenny and David in Sheffield, we found it's not the case actually. So our Lubrin nanoparticle shows the poor fluorescence quantum of 3%. And by just adding this third component DBP, we could improve the fluorescence quantum for more than 20 times, and it becomes 61%. And Fred definitely happening from the fluorescence spectrum. But the question is whether it outcompetes with singlet fission or not. So before addressing this question, we checked the Lubrin transient absorption of these Lubrin nanoparticles. So this Lubrin nanoparticle shows the singlet fission with a time constant of 10 picoseconds. So it's definitely not intersystem crossing singlet fission. So after singlet fission, we further observe some evolution coming from the change from the strongly correlated single TD pair to the weakly correlated pair, and also spin evolution to other spin multiplicity. So and then we add the third component collector, the DBP, So here, surprisingly, we observed almost no effect on the singlet fission dynamics. So, and after singlet fission, DBP singlet was observed. So singlet fission dynamics was not affected, so still it happens at 10 picosecond. And after that, actually the fret with time constant of 50 picosecond happened. So singlet fission is too fast, so fret cannot outcompete. But still, this side component, the DBP corrector can improve the fluorescence continuity. So what's happening here? So actually, the after singlet fission, as I mentioned, the triplet, it takes more time for the triplet to separate from strongly correlated TD pair to weakly correlated and then free triplet. It takes time. So within 4 nanoseconds or so, it's still staying very close. So still still geminate recombinations happening. And actually, this is much slower than the fret. So actually, fret cannot outcompete with the singlet fission, but it can outcompete with free triplet generation or triplet pair separation. This is very important because after triplet pair separation, triplet may be quenched by defects and it's lost. So this is important to the role of the singlet energy corrector is to suppress such a triplet pair separation and triplet loss. And with this improved three-component system, we combined with perovskite solar cell, and we observed the nice near-infrared sensitivity to perovskite solar cell by using this near-infrared to the visible upconversion. Although we need to decrease the excitation intensity further, but it's a kind of that is the very important future work direction. So with that, I want to conclude my talk. So today I mainly introduce 3 topics. The first in epoxy resin, it's very important to use the high acceptor concentration over 38%. It's important to avoid the triplet back energy transfer to achieve the highest upconversion efficiency over 10% in the rigid polymer material. And second, I also showed that it's also important to avoid a singlet back energy transfer by adding the third component collector. And third, in the specific lubricant system, not only back energy transfer, singlet back energy transfer, but also a singlet fission is we need to think. And the collector, in this case, collector have cannot outcompete with singlet fission, but compete with the triplet pair separation. So it's this also suggests us that eliminating the triplet quenching defects can also be the alternative strategy when we use the singlet fission material for the upconversion. Okay, with that, I want to thank to all my group members and my great collaborators and also my funding. And unfortunately, I'm showing you the recorded video. So if you have any questions, please send me an email or chat message or any other methods by using this MRS platform. So thank you very much for your kind attention.